welcome to today's crash course on concentration. This crash course is mainly meant for secondary 4 students, but if you're in secondary 3, everything in here applies to you except when we get to the part about parts per million. So in part 1 of this video, we're going to be talking about concentration, its definition, factors that affect concentration, as well as its formula. We're going to talk about concentration in grams per liters, as well as in ppm, parts per million. And then when we hop over to part 2 of this video, we're going to talk about concentration and percentage, as well as different concentration conversions with different units of measurement. So let's dive in. So before we jump into what a concentration is, let's talk about what a solution is. And a solution is a type of mixture where one substance, which is the solute, is dissolved into another substance, which is the solvent. So if we take the example of salt in water, and we dissolve salt in water, salt being the solute, and water being the solvent, it will dissolve and create a solution. And this solution is water-based, so we call it an aqueous solution. But not all solutions are liquid. We have some solutions that are gas. So for example, if we are talking about air, and we have nitrogen and oxygen being the solute, nitrogen being the solvent, that is a mixture or a solution of air. And then we also have solid solutions, like for example, metal alloys. So we have to keep all of those in mind when we're talking about solutions. So terminology is really important when we're talking about concentration. So concentration is the ratio between the amount of solute and the total amount of solution. And the total amount of solution is our combined solute and solvent. So if we add those two together, we get the total solution. So if we look at 100, we have 100 particles here. As you guys can see, the ones that are in yellow, that is our solute per 100 particles of solution. It's not comparing solute to solvent. We are absolutely saying that there is 1% solute in 100% or 100 particles of solution. So it's really important to remember that it is a ratio between the amount of solute and the amount of total solution. What concentration is illustrated in this diagram? Is it A, 7 particles of solute per 43 particles of solvent, B, 7 particles of solute per 43 particles of solution, C, 7 particles of solute per 50 particles of solvent, or D, 7 particles of solute per 50 particles of solution? The answer is D. So that's when we jump into factors that affect concentration. So the concentration of a solution can be changed by varying the amount of solute and the amount of solvent. So for example, again, if we take our salt water solution, if we add more water to that solvent, the amount of solute, the amount of salt is not going to change, but the amount of solvent and the total solution is going to increase. So when that happens, if we increase the amount of water, we are going to dilute the solution, which means the concentration is going to go down. Now, if we leave that solution out on the counter somewhere, some of that water over a couple of hours will evaporate. And so what happens is that the water, which is a solvent, is going to decrease. And so our concentration is going to increase because there's less water particles and more salt particles in our solution. Increasing the amount of solute leads to an increase in the concentration of the solution. True or false? The answer is true. So believe it or not, the amount of solute has a direct impact on the effect of concentration. It is a factor that influences concentration. So if we add salt to our solution, the concentration is going to go up. And if we add, or if we remove salt, or if we add more solvent, then what's going to happen is the concentration is going to be diluted and it's going to go down. So our amount of solute is directly correlated to our effect on concentration. Amount of solute goes up, so does the concentration. Amount of solute goes down, so does the concentration. So there is a mathematical way to calculate concentration, which we're going to explore now. So we're going to look at this formula here, which is concentration is equal to mass divided by volume. And so it's really important in concentration when we're dealing with any type of formula that we always look at our units of measurement. They are the most important part of the entire process. So first bit, the C represents concentration, and concentration is measured in grams per liters, grams per milliliters. And then we also have mass, and the mass is of the solute. Okay, so mass is a mass, grams, milligrams, kilograms. And then we also have volume, and the volume of the solution is measured in milliliters and liters. Now, to manipulate this, because sometimes we won't just be solving for concentration, we might be solving for mass, or we might be solving for volume. So what you can do with any time that you have a 3-variable formula is you can draw a triangle, and you can put we'll put the C here, and then we have our M, and we also have our V. And so what you can do with this, it helps you manipulate to solve whatever variable you need. So if I want to find concentration, I hide it with my hand. Concentration is mass divided by volume. If I want to find mass, it's concentration times volume. If I want to find volume, it's mass divided by concentration. And so that's a really cool way to help you manipulate the formula to solve any value in this formula. So let's figure this out using a first example. So in grams per milliliters, what is the concentration of a saline solution prepared by dissolving 9 grams of NaCl, which is sodium chloride, salt, in water to obtain 1 liter of solution? So remember, we always need to write down what we know, and units are important. We know that concentration, even though we don't know what it is in the question, that's what we're being asked, we know that the unit of measurement for concentration is grams per milliliters. Our mass is in grams, so that's good, that's a check, but our volume is in liters, so we need to turn that volume into milliliters. So we are going to multiply by 1,000 milliliters and divide by 1 liter. The units are going to cancel out. So we get 1 liter is equal to 1,000 milliliters. Remember, concentration, grams per milliliter. So now my units match up. Remember, I told you at the beginning, we need to make sure our units match up. So we use our formula. Concentration is equal to mass divided by volume. We're looking for concentration. So 9 grams divided by 1,000 milliliters gives me 0.009 grams per milliliter. So the concentration of the solution is 0.009 grams per milliliter. Let's go for a second example. This time we're going to try and find something different. Sweetened water for hummingbirds should have a concentration of 0.2 grams per milliliter. What mass of sugar is required to prepare 55 milliliters of this solution? So again, we write down what we know. The concentration is given to us in the question, so 0.2 grams per milliliter. We don't know the mass, but we do know that it has to be in grams. And then our volume is 55 milliliters. So our volume units match up. So we're going to find our mass. So it's concentration times volume. So we're multiplying. So mass is equal to 0.2 grams per milliliter times 55 milliliters. And that gives us an answer of 11 grams. So the mass of sugar required for this solution is 11 grams. But sometimes the concentration of particles is so incredibly small that we need a different type of unit of measurement. Like, for example, when scientists are trying to take readings of pollutants in water or in air, and that measurement is called parts per million, ppm. And it's a unit of concentration that indicates the number of particles of solute that are found in 1 million particles of solution. So it's a very small amount of concentration. So for example, in an air sample, it contains 1 million particles in total, which include 52 particles of pollutants. So the concentration of pollutants is 52 parts per million, or 52 ppm. So very small concentration. So when we're calculating parts per million, or ppm, we're going to deal with 2 formulas. The first being aqueous solutions, so like dissolved solutions. So when we're talking about it, we're talking about concentrations measured in ppm. Our mass of the solute is in grams, and our volume of the solution is measured in milliliters. And so as you can see here, it's pretty much the same formula as our concentration formula. Concentration is equal to mass divided by volume, but we're timesing it by 1 million because remember, it's parts per million. And so if you look at the bottom here for our conversion, 1 ppm is equal to 1 gram divided by 1 million milliliters. But if we go to this side, this is where we're talking about solid or gaseous solutions, where we're going to use grams to calculate our ppm. So our concentration is the mass of the solute divided by the mass of the total solution times 1 million, where our concentration is in ppm, our mass of the solute is in grams, and our mass of the solution is also in grams. So units of measurement, again, super important. So 1 ppm is equal to 1 gram over 1 million grams. So we have our aqueous solutions and our other solutions. 2 very different formulas, but at the same time calculating that concentration. So let's practice with the first example. Health Canada recommends that the concentration of fluoride in drinking water does not exceed 1.5 parts per million. The authorities in a small town plan to dissolve 160 grams of fluoride in the 120,000 liters of emergency water reserve. Will this water respect Health Canada's guidelines? So we need to write down what we know. We know that our concentration is going to be in ppm, parts per million. The mass is given to us, it's 160 grams. And we also have 120,000 liters. Now remember, concentration in an aqueous solution is grams per milliliter. So we need to turn those liters into milliliters. Okay, so we're going to times it by 1,000 and divide by 1 liter. So we get 120 million milliliters. So we're going to use our formula. We're going to use concentration is equal to mass divided by volume times a million. So we get concentration is equal to 160 grams divided by 120 million milliliters times a million. And we get an answer of 1.33 parts per million. So yes, the emergency water reserve respects the guidelines because 1.33 parts per million is lower than 1.5 parts per million. So let's dive into a second example. A gaseous solution is prepared by combining 1.2 milligrams of solute with a certain mass of solvent. The final concentration of the solution is 60 ppm. What mass of the solution was prepared? So we need to write down what we know. We know that the concentration is 60 ppm. We know that the mass of the solute is 1.2 milligrams, but I like grams. So we are going to convert that into grams. So we're timesing it by 1 gram, divide by 1,000 milligrams to get 0.0012 grams. And we're trying to find the mass of the total solution. So we're going to use the concentration mass solute divided by mass of the solution times a million formula because we're not dealing with an aqueous solution, we're dealing with a gas or we're dealing with a solid. So we're going to move over, we're going to put everything in our formula. 60 ppm is equal to 0.0012 grams divided by the mass of the solution, which we don't know, times a million. Based on the following equation, what is the mass of the solution? 60 ppm is equal to 0.0012 grams divided by mass of the solution times a million. Is it A, 0.050 grams, B, 20 grams, C, 0.0000072 grams, or D, 0.00114 grams? And the answer is B, 20 grams. And so that's the solution to our problem. We put it in our formula. We get mass solution is equal to 0.0012 grams divided by 60 parts per million times a million. And we get an answer of 20 grams. So the mass of the solution to this problem is 20 grams. So here's a little tip for you. The mass of the solution includes the mass of the solute and the mass of the solvent. So we can use subtraction to find any missing measurements. So if you remember, mass of solution equals mass of solute plus mass of solvent. So if you put those together, you get everything. So if you want to find the mass of the solute, for example, you would just use the mass of the solution minus the mass of the solvent, or vice versa. So you can play around with this as well. And so there you have it. Everything you need to know about concentration in part 1. So remember, we talked about the concentration, so the ratio between the amount of solute and solvent. We talked about how when the solvent increases in a solution, the concentration will decrease. And if the solute increases, the concentration will increase. We also talked about our formula and how concentration is measured in grams per liter. Mass is in grams, volume of the solution is in liters. But we also talked about our parts per million in solutions that are aqueous and all the other solutions. So make sure that you hop over to part 2 to check out concentrations with percentages, as well as different concentration conversions. I'll see you there.